host in SolidWorks, filling in for helping out Tramek today with this short presentation, tips and tricks on no penetration contact. So I just want to give you a heads up, before I dive into showing you some of the tips and tricks, what we do in terms of structural or mechanical validation tools. So I'm not going to talk a lot about on this particular slide, but kind of to give you an idea, we have several flavors of our structural simulation package, starting with SolidWorks Simulation Standard, as you can see on the left side. And with this, you can actually do static analysis or linear stress analysis. A nice feature is trend tracker analysis. You can also do some motion analysis if you're interested in understanding the kinematic or the dynamic behavior of mechanisms where you might want to actually size motors, gears, actuators, and so on. This can be a nice tool set to have. And then also with Simulation Standard, you get to do fatigue analysis, which helps you to predict the durability of or the life of your product. So that's kind of a nice little package to help you get started with structural simulation. But then from there on, you can actually move on to SolidWorks Simulation Professional, where you can actually do other things on your design to paint the full picture, like, for example, frequency analysis, buckling, thermal analysis, optimization, and also 2D simplification. We also have a lot of virtual connectors, which makes it really easy for you to be able to simplify geometry when it comes to analyzing things like a bolt and nut or edge weld connector or a pin connector. So without accounting for the geometry, you can actually take into account the effect of those guys on the rest of the assembly. We also have, so you can see that we have several types of analysis you can do: pressure vessel, drop test, submodeling. So if you're using Simulation Professional and you're on maintenance, so you can actually access a material web portal where you can have access to a variety of information, and you can download the mechanical, thermal properties, maybe fatigue data, stress strain data for certain materials you're looking to simulate from this particular web portal directly into a format that can be used inside SolidWorks Simulation. Load case manager is another way, a nice way to kind of simulate different what-if scenarios. What if I have a certain type of loading or a combination of different loads? How does it affect the performance of my design? So it's a nice little tool set as well. Then our highest level simulation package is called Simulation Premium, and this is actually where you take a deep dive into doing some very complex physics, but again with the ease and intuitive workflow of SolidWorks and SolidWorks Simulation. So you can do things like nonlinear analysis, a dynamic analysis, which kind of can be broken down into time history, harmonic, random vibrations, shock, and so on. And also we have composites with Simulation Premium. So this is kind of a quick overview of what we do when it comes to structural simulation. Now I know that most of you on the call have or are looking at our simulation tools, and today's agenda is obviously to actually look at some tips and pointers when it comes to simulating the physical behavior or the interaction between multiple parts or multiple geometries in your assembly, which we call as contacts or no penetration. So with that, I'm just going to minimize this, jump straight into SolidWorks, and I'm just going to go ahead and show you. I have two different examples to showcase. One of them is actually a full three-dimensional model. The other one is 2D model. So you'll see a difference as to how you can use contacts in both scenarios, and again we'll cover some other tips and tricks there. So the first example is more like a medical example, so hopefully you can, I just want to confirm with Dana that you can see my SolidWorks screen, and that way, I can, it gives me, it basically establishes that all of you can see my window. So Dana, can you just give me a quick okay? Can you see my screen? Dana, can you hear me? Okay, so I saw some feedback from some of the...
I'm sorry, I was muted.
Not a problem. Yeah, it looks like some of the users, the audience actually responded to the fact that they can in fact see my screen, so that's great news. But again, so basically, this is kind of a medical snap fit assembly where we actually let me show you the full model, and this is what the full model looks like. It's a pretty simple assembly operation that we're trying to accomplish. And what we have is actually a plunger here on the back end, which is the blue body, and then we have the main body. And what we want to do is kind of, push this plunger through the main body so that it slides all the way and kind of snaps into place. Okay, so it's a simple assembly operation, but again, how do we accomplish the physical interaction? Well, we're going to use some contact conditions. But before I even dive into actually, doing setting up a simulation study, one of the things I always recommend to my users is that take advantage of any kind of symmetry you can take. So, for example, in this case, if I rotate the model, you can see that if I take half the model is perfectly symmetric on the other side. Okay, so I have two areas where the snap-on action is going to take place. So this actually gives me the ability to actually go ahead and simply take half the model for analysis purposes. So again, keep in mind when you're actually simulating any kind of contact conditions, especially no penetration contact, which is going to account for the physical interaction, there's a lot of iteration the program is going to do behind the scenes to simulate the contact behavior. Because technically it's a nonlinear problem when you specify contact, and so with nonlinear problems, there's a lot of iterations that's taking place behind the scenes because the program has to figure out the contact area. The load transfer between the two bodies might actually be different depending upon how much contact area is actually happening at any given instant of time. So we can actually go ahead and simulate the behavior, and so everything starts off with a study process. So study is nothing but a great way to tell the program what are you trying to accomplish. So it could be something simple as linear static analysis, or it could be you're concerned about heat transfer or frequency analysis, buckling, or in this case I'm going to choose nonlinear analysis. And the reason was because I want the contacts to be simulated as accurately as possible. And like I said before, there's a lot of iteration that goes on behind the scenes, and for that iterative solution, we want to make sure that we get the right answers. So the program actually has to take smaller time steps, especially when the contact areas are really small, and we need to capture the exact sliding operation that requires us to do a nonlinear analysis if required. I don't have to do this per se, but if it was me, I would actually start off with a nonlinear analysis, and I can always do a static analysis to get started, like for a quick first pass analysis, get some answers. But then for the real or the accurate results, I would actually end up doing a nonlinear analysis, and I'll actually talk a little bit about why exactly nonlinear. One of the reasons is contact, but then I can always get away by doing a linear static analysis. But I'll come back to that a little bit later on. So let's get started with the nonlinear analysis. Let's call this as maybe snap fit test, and there you go. So I'm not going to go through the entire process of setting this problem up because I know the time has really started a little bit late, and you guys are looking for really the tips and pointers. So I basically let's go ahead and jump into contacts right away. So when it comes to contacts, you can actually go ahead and do a few things here. There's something called the global contact. So if you come under component contact, there's something called global contact. Let's go and take a look into what the global contact does. Now, typically, there are two types of global contacts: bonded and allow penetration. Okay, so what you can do is allow penetration is something very rarely used, but bonded is kind of the default setting. And again, with bonded, what you can do is you can basically tell the program if it's compatible, if the mesh should be compatible or incompatible. So really in cases where you might have overlapping surfaces and the overlapping surface might be kind of lead to some sort of a sliver face or maybe a zero, maybe some sort of an edge contact, you might actually want to switch to incompatible mesh, because those are the type of scenarios where you have sliver faces and things like that, which can actually cause the meshing process to fail. So compatible is kind of the default option, but in case you run into issues where they are using global bonded and the meshing process fails, switch to an incompatible mesh and see if that actually helps out. So what the difference is very simple. Compatible actually takes the smallest area. Let's say you have two surfaces touching each other. The compatible mesh actually projects the smaller area onto the larger area, and it basically uses that for analysis. Now, when you do incompatible mesh, it does not do any kind of imprinting operation. So it basically meshes the two touching faces independently of each other, and that way the meshing process goes through. So again, keep that in mind that when you have issues with compatible mesh, try to switch to an incompatible mesh and see if that actually helps go past the meshing issues. All right. So bottom line is when it comes to global contact, my recommendation is always keep it as bonded, and then from there on go and apply some of the local contact options. So here, for example, I can do contact set. So for example, I can say, all right, let's go ahead and pick the faces of the two parts that might technically come into contact with each other. So for example, I can say, yeah, I know that this chamfer face on the plunger, this guy, and this guy, and maybe this guy. So these faces might, and maybe even this guy over here. So I can actually select all the faces that I think on the plunger, and you can see that I have about 7 faces selected, and I know that those faces are going to come into contact with, let's say, the faces on the main body. So I'm going to select this face over here on the inside of this hole, and then I'm also going to come here. I know the snap-on should take place right here in the slot area on the main body. So I'm going to select all those faces that will technically or may come into contact with those faces on the plunger. But that's pretty much it. When it comes to contact selection, that's kind of the select geometry selections. So you have no penetration, bonded, allow penetration, shrink fit, and so on. And in this case, today's focus is no penetration contact. So you can see that when it comes to being able to select that define the no penetration contact, it's a simple geometry selection. You can include friction. So again, this is what we do is we simulate the Coulomb friction. So in case there's any kind of friction on surfaces, it's not really perfectly smooth. You want to include friction in your in your contact. You can do that as well. Let's talk a little bit about advanced options. Now, I would think that you shouldn't have have to come into this portion of the contact definition to change any options. But just to give you an idea as to what these options actually do. So you can see that we have node to node, we have node to surface, and surface to surface. All right. So basically, node to node is something where you have two faces touching initially, and those two faces transmit the load only in tension or compression. And so there's no shear load that's going to be transmitted between the two faces. And plus, in this case, what we are assuming is the two faces never can come apart. So they should be always touching each other. Okay. So it's kind of limited, right? Because number one is it's going to only transmit the loads in tension or compression it cannot actually account for any kind of shear loading between the two surfaces, like sliding loads. And the third one is, the two faces cannot lift off, and that's kind of, so really it's applicable to a very few a subset of problems where you want to actually run the problem really fast, and node to node we are solving for, each node on one surface is actually connected to a corresponding node on the other surface. Okay, so it's kind of a one-to-one relationship there, and that's why this type of contact will run the fastest. But again, I talked a little bit about the limitations of where this can actually be used. So typically, you would actually look at using node to surface or surface to surface. So node to surface is the program behind the scenes is actually taking each node on one surface and actually tying that up with a bunch of nodes on the other surface. So basically we are solving for more equations, but again, it's a little bit more accurate than node to node. And node to surface, it also runs real fast, but again, the limitation there is it can actually cause some sort of if you have some sort of a rotational or a torque effect on your system, it can actually break down pretty quickly. And really, usually I recommend node to surface in problems where you have let's say you have any kind of a point to surface contact. Think about it that way. So if you have like a cylinder surface coming and touching, let's say, a flat surface, you might actually want to use node to surface in that scenario. Okay, so surface to surface is kind of the top level, and I recommend this to be kind of the default setting. Use this all the time if you can. But again, the trade-off is, it takes much longer than node to surface, but it will actually give you the most accurate results when it comes to simulating contact problems. So again, so what is happening here is we are taking each node on one surface and we are tying it with a bunch of nodes on the other surface, and likewise, vice versa. So we're taking each node on the second surface and tying it with a bunch of nodes on the first surface. So you can see that, for example, I have all these different faces on my plunger body selected, and I have a bunch of faces here selected on my main body. So if I use surface to surface, you can see that there's a lot of permutations and combinations, and a lot of constrained equations that we are solving behind the scenes, because each face here, what we're saying is each face, let's say face number 1 on the first selection box can actually interact with face 8, 9, 10, and 11 on the second selection box, and likewise. So you can see that there's a lot of what we call as constraint equations that are going to get created because we are using surface to surface contact, and that can actually take a lot of time. But again, when I say a lot of time, it doesn't mean that if I use node to surface, if it takes like 30 minutes versus surface to surface, it's probably going to take about let's say 45 minutes. So this and one of the good news is that surface to surface also converges really well in majority of the contact problems. Okay. So again, the node to node and node to surface also comes from legacy days where we had initially just node to surface, and then in the last 6 or 7 years when we started introducing surface to surface, the top 2 options actually ended up being there because some of the customers were actually using this to solve the contact problems on their designs. Again, if you ask me honestly, like what is the right one to use, number one is it's important for you to understand what's the difference. So hopefully now you know kind of the difference. But if you have to use a particular type of option, I would suggest surface to surface contact. All right. So pretty much when it comes to defining contacts, no penetration contacts, that's kind of a big deal. using surface to surface. Now, one of the other types of contact option is if you look here, what I just did was I switched from manually selecting the contact sets to automatically finding the contact sets. So here, if I have faces touching, that's great. If I have non-touching faces, I can also specify a range like a min and max clearance between so where the program will detect the minimum distance between two faces that might be close to each other and kind of display that face pair over here. So let's try what happens when I select touching faces. So I'm just going to grab this guy over here and say, okay, those two parts are go ahead and find any contact sets. So you can see that it does not display any contact sets here, okay, because literally no faces between the plunger and the main body, then nothing is touching initially. So if I use non-touching faces, and hopefully this will actually locate some things, so you can see that it'll actually go ahead and tell me, oh yeah, it actually found one set of faces. If I zoom in real close, you can see that it's automatically finding out that kind of that circular face is actually is close to that flat face of interest. So again, a great way to actually automate let the program do all the hard work when it comes to selecting the contact face pairs of interest. Then here what I can do is I can say, yeah, go ahead and add that contact pair to my simulation feature tree, or I can change or I can specify what type of contact should it be. Okay, so the program tells us these are possible pairs of faces that might come into contact, but then I can control also what type of contact should happen. And then let's do a transparent view so you can clearly see it's that face pair, this the circular face on the plunger and the flat face on the main body. That's what it's detecting right now, and that's based on the tolerances, min and max setting over here. And so if I change that, it might detect, it might give me another set of faces that might come into contact. Now, another trick here that I typically do is, let's see, let's go ahead and take the transparency. A lot of times, this is a simple two-part assembly, right? But a lot of times it might be really, you might have a zillion parts in your assembly, and there might be, faces that might come into contact all over the place. So one of the things I typically recommend is if you use exploded view. So what I would actually do is I'm going to go ahead and say, all right, let's go ahead and explode this view. And click OK. So when I explode the view, we kind of, a lot of times things might be overlapping, touching each other. It might be just difficult to kind of, make the face selections manually. So this actually is another nice way to kind of, separate out all the parts in your assembly. And because then I can now define my contact in a much easier fashion. So I can say, yeah, now I know that these faces, for example, let's see, yeah, these faces can come into contact. So it allows for a clean and a nicer way of selecting the faces, making sure that we don't miss any faces that might come into contact with each other. So you can see that I can rotate, I can zoom in, and I have a clear access to all the faces I want to select for my contact definition. So use this, use an exploded view wherever possible, just for when it comes to defining your contact. Makes life real simple. So once I do that, I can collapse the view, or I don't have to do anything. I can mesh it, I can run it, because the program is eventually going to solve the problem in the collapsed view state. So you're not actually compromising. The program simulation is not going to assume that the two pieces here are going to be far apart, like in an exploded view. So let's go here to the full study. So what I have here is plastic materials, acrylic, medium, high impact. I have contact sets already defined, and I have some fixtures and so on. One of the things that you would actually want to do with contact problems is, a lot depends on the contact areas. So a lot of times you might set up the contact correctly, but it may not actually converge to a nice solution just because the mesh might be really coarse in the contact areas. So typical recommendation is to go ahead and apply some mesh controls in the contact area. So for example, you can see that in my example, I have a bunch of faces on the plunger that's actually selected for local mesh control. So that way I can tighten up the mesh in those contact areas and make sure that the number one, a tighter mesh actually represents the geometry more accurately, and number two is it accurately models the load transfer between the two faces. So having a detailed mesh in the contact areas actually helps the solution converge nicely. So keep that in mind when you're defining contact problems. You might actually want to define a nicer or a little bit detailed mesh setting or control in the contact areas. Let me go back to the contact definition itself. So the first one, I should have talked about this a little bit earlier, but the first one here, we call that as a source dialog box, or the source selections. And the bottom one over here is actually called the target selections. So the source areas, so there's a couple of things that you might actually want to keep in mind when it comes to selection of the faces, the geometries in the source dialog box. So number one is that geometry has to be a softer material, okay, compared to this guy over here at the bottom. The source geometry has to be much smaller, or if it has a high curvature or a radius, then you might actually want to select that in the source dialog box. Okay, and any larger area, if the area is really large and flat, that actually goes in the bottom selection. Okay, so a couple of key things here. If the material is softer, then you select the faces or the geometry corresponding to the softer material on the top, and then if the material is more stiffer, then you select the geometry on that material in the bottom selection. Okay, so hopefully that is clear, because that's kind of a lot of times you might actually just define the contact, and but then if you select the softer material in the bottom, it can actually lead to any divergence issues. And you might think you have set it up correctly, but the solver might actually come back with things like the contact not converging, and one of the reasons could be that you have not defined the contact selections correctly, in terms of the source and the target dialog box. Okay, so keep in mind the top one is called the source, the bottom one is called the target, and the top one has to be the softer material. It has to be the smaller area, and any kind of radius or curvature that you are looking at, that has to be selected here on the top. Okay. And also, in general, when you're solving contact problems, you might actually want to select your direct sparse solver. So if you go to study options, study properties, the general recommendation is use the direct sparse solver, especially when you have friction in your contacts. You use the direct sparse solver. Okay, so FFE plus works great. It might actually run fast, but then if you have friction, it does not work really well. So any kind of contact problems, I would certainly recommend to use the direct sparse solver, or in 2015 we introduced what is called as Intel direct sparse. One of these two solvers will actually help you out when it comes to simulating contact problems. Okay, so this is kind of a quick overview of on a 3D model. But what I want to segue into is, you might be doing this contact multiple times and multiple studies. And you might be selecting the same faces, right? So one of the things I typically take advantage of is, so for example, let's go to an exploded view, and this will actually help you out, especially when you're defining contacts and or maybe even applying mesh controls. So let's go ahead and see, for example, let's go ahead and select these faces one more time. So I'm going to select all these faces in the plunger. And you can see there's a small step here. I'm going to select that face. And so I got all the faces on my plunger selected. And now I can go ahead and say, if I right mouse click, I have an option called Save Selection. And I'm sure, like, those of you who are on SOLIDWORKS 2015 might actually be using this or might be aware of this. But this is actually what happens. When I do a save selection, it actually creates, in the SOLIDWORKS feature tree. Let's go ahead and expand this really quick. So you can see that I have all these faces selected and created as a selection set. So let's call this as plunger. Okay, there you go. Let's do this. And now what I can do is I can say, all right, let's do the same thing on the main body over here. So let's select this face over here. Maybe it might come into contact with this on the face over here. Let's go to the slot area, and I'm going to grab all these faces over here, and then I'm going to do the same thing. Right mouse click and save selection. It actually creates a second selection. Let's call that in my SOLIDWORKS feature tree, which is on the left side of your screen. You can see that second selection set. I'm going to rename that as main body. So now, let's say I created this study, and now I want to actually go ahead and apply my local contacts, or if I want to apply mesh control. So I can simply fire up my contact dialog box, and then I can say, all right, I'm not going to go to the graphics area and select each face one by one. I already got that predefined, so I'm just going to go ahead and select this plunger selection set, and watch what happens. It automatically grabs all those faces, and that's really cool. And I think it's a highly productive environment now, because we take advantage of what we can do in an integrated environment. Just because we're taking advantage of SOLIDWORKS options as we are doing simulation. And so now I'm going to come back into my contact and highlight my bottom selection set, what we call as a target, and then I'm going to select main body from my flyout manager here, and watch what happens. All the faces belonging to the body, main body, gets selected automatically. So I can simply click OK, and there you go. So same thing comes with mesh controls. If I want to apply refine mesh control in contact areas, and as I alluded earlier, in terms of when you're solving contact problems, you want to actually have a local mesh control. So now, instead of going and selecting each of those faces one by one, I can just come here to my selection set in the flyout manager, select plunger. I can see that it's selected all the faces, and I can say, yeah, that probably needs about 0.5 millimeter element size. Click OK, and you're all set. Okay. So here I can just say create a mesh, click OK, and you can see that right at the bat I have a nice detailed mesh in the on the faces of the plunger that might actually that are going to participate in the contact process. Okay. All right, so I'm just going to close this model, and I'll take 5 more minutes to actually show you a second model, which is more like a 2D analysis but involving contacts. So let's go ahead and do that, and then we'll actually have a quick Q&A session to answer any specific questions you might have. Let's go here to this packaging model. Okay, there you go. So here again I have a simple 2-part assembly. It's more like a snap fit operation. It's a 3D model. But I can really take advantage of the fact that it's a plane stress type of scenario. So what I can do is I can just go ahead and switch to, and in case you haven't tried 2D analysis or 2D simplification, here is how it works. when you start off with a new study, you can see I have, let's say, a static analysis, and right at the bottom I have this 2D simplification. So here I can simply check that and click OK, and what happens is it brings me to the next dialog box where I can go ahead and say what type of 2D analysis do I want to do. Is it plane stress, plane strain, or axis symmetry? So plane stress, for example, here I can say, all right, let's go and grab a section plane, and I'm going to use my, let's say, my front plane. So you can see that's automatically extracting the section here, and then I'm going to give it a certain section depth, and that section depth is nothing but the same as the the overall length, or the direction in the z direction length. Okay, so I can just say that's probably around, let's see what the length is. Okay, so let's say that's about 15 millimeters. Click OK, and there you go. So it automatically extracts the 2D section for me, and I think this is really powerful. Like I said, on the first model that I showed you, I took half the model for the assembly analysis because I can take advantage of symmetry. And in this case, I took advantage of a two-dimensional scenario here called plane stress, and I simply took a section for my analysis. Okay, so that way I can actually go ahead and simplify my analysis, simplify my meshing time, and reduce my solve times, and I can get more detail in terms of the mesh itself here. So so for example, I can say, all right, let's go ahead and create a mesh, and let's see what it looks like. So here I see it's created the mesh, but then I can say, well, that's not enough. I need a nice looking mesh in the contact area. So I can apply some mesh controls, and again, in this case, I have some selection sets. So you can see that I have contact sets 1. Yeah, not that guy, sorry. So this guy over here. So you can see that right at the bat, I know before I created the simulation study, I actually created this contact sets, and all I have to do is grab all the contact sets, all the edges, and by the way to do that is simply highlight the contact set here in the flyout manager. So it automatically grabs the required edges of interest, and I can say, yeah, let's mesh that a little bit finer, and let's create a mesh. So it's a little bit better than before, but again, you can see the power of using these selection sets when it comes to defining mesh controls or contacts. Let's hide these guys. There you go. Now, when you're dealing with two-dimensional analysis, or in this case, plane stress analysis, again, one of the things, the way you define contacts does not really change. So here, if I want to define contacts, it's exactly the same, except that instead of a face, I probably am going to be selecting edges. So here, for example, I can say select this edge. Let's select the tangency condition. So I'm saying all the edges here on the top body are probably going to come into contact with this guy here. Or instead of a loop, I can select specific face. This guy, this edge over here, this edge over here, this edge over here. So again, a simple way to define that. That's one way of looking at it. The difference between a 3D model and 2D model is just instead of a surface, you're selecting edges. Now, in 2015 simulation, we introduced what is called as a self-contact. And self-contact is nothing but a great way to kind of simulate. There might be scenarios where the same surface, like you might have a spline surface, maybe some sort of a threaded connection where the threaded surface is one single surface, or you might actually have some sort of a bellows scenario where the same surface might actually come into, or the edge might come into contact with itself. So when that scenario happens, you might actually want to define a local contact and check this box called self-contact. So in this example, so let's say for example, as this thing is bending, you can see that, let's see, what would be a good edge over here? Yeah. So let's say for example, as you're pushing this and this top piece is actually bending, this curved surface over here might actually get squeezed so much that this endpoint might actually end up touching this endpoint. So what I can do here is I can say, yeah, this curved edge is probably going to self-contact. I don't know for sure, but if you suspect that that scenario might actually happen, you can select this type of contact where you select, the workflow does not really change. All you're going to do is check this box called self-contact, and there you go. Okay. So again, a great way to take advantage of some of the new options in 2015, like the self-contact, or maybe in SolidWorks we have the selection sets. So being able to take advantage of what we can do there to actually avoid the quirks and pains of doing multiple selections, or being able to, or having to reselect the same geometry again and again and again. Take advantage of selection sets. Okay, so I'm actually going to stop here. And kind of take some questions. You've probably seen some some of the tips and tricks, some brief. We took a little bit of technical dive into looking at different types of contacts just in the given time frame. But I'm going to actually stop here and let you guys ask me any questions. So hopefully this was worth your time. Thanks for listening in. But let's go ahead and see if any of you have any questions. And feel free to
I'm sorry.
Yeah.
Go ahead.
No problem. I'm just looking at questions, so I just want everyone to ask any kind of questions, specific questions, things they may not have seen today in this presentation. But okay, so the first question is, let's see, can you provide the address for the material web portal? I can certainly send you that link. I don't have it on top of my head, because what happens is when you, so I'll show it to you live so you can see what I mean by that. So when you do when you access the material dialog box, you can see that right here at the bottom there's a link that says click here to access more materials using the SolidWorks material web portal. And this is again, you as a user, you will have access to this when you have let's say the Simulation Professional package, and plus you're actually on maintenance. So if I go ahead and say, so you can see that when I click the link, it displays this message, and you can clearly see that you need to have a license of Simulation Professional or higher, and so on. So when I click OK, hopefully it takes me to the that web page which I just showed you, which I just talked about. But here is the web page. It's a long list. It's a long link. So I think the main address is my.materiality.com, and I'm just highlighting this on the web page address bar. And if you want, you can take a note of that. Maybe you have to type in this guy here, my.materiality.com /SolidWorks. And I think that'll actually take you to the login page. Otherwise, if you open up a web browser and let's say type in that directly, it actually takes you there, because it's smart enough to know that it's actually coming from my SolidWorks license, which is on subscription. But try this. Try the link and see if it works out. But again, I showed you. The way I would actually recommend accessing this is from within the material dialog box, and right on the bottom left corner there's a link to access that material web portal. Okay, so that's a good question. Hopefully that answers the question as well. So the second question is, why not 1/4 of this model? It has 2 planes of symmetry, and that's a great point. Absolutely, you can take 1/4 the model. Because it does have 2 planes of symmetry, and in fact 1/4 the model can actually be a much better option, because you're just analyzing. That's going to dramatically reduce your meshing time and hence your solution times. Again, like I said, the first thing that typically you want to do when you start working with simulation and your design is see if there's any way to take symmetry. It could be 1/2, it could be 1/4 or 1/8, or if there's a way to simplify it into a 2D simplification problem, great, take advantage of that, because as soon as you throw in the contact definition there, that's going to add on to the analysis time. So anywhere you can simplify the geometry for with contacts, it's certainly going to be a huge time saver for you. I'm not sure. The next question is, why did the upper model or body section translate downward? Not sure if you're talking with respect to the 2D one or the 3D one. Let's come back to that question a little bit later on. I'm not fully understanding that question, and maybe we can take this offline as well. So the next question is, how do you know when to use 2D or 3D analysis? Okay, so that's a great question. So you can actually do 3D analysis pretty much on anything, right? So when it comes to doing 2D analysis, there are you can look at a couple of golden thumb rules, I would say, is see if there's a constant cross section. Okay, so when I showed you plane stress, and in plane stress, what happens is one dimension is much shorter than the other two. So the thickness in that case, in the assembly that I showed you, is much smaller than the width and the height. So when you're looking at cross sections like that, think about if there's a way to take 2D, do a 2D analysis. Okay, if you have any kind of a structure that's kind of a revolve, has a single axis of revolution, then you might actually want to take advantage of 2D analysis there as well. Okay, so there are certain rules that actually will help you kind of translate a 3D problem into a 2D problem. So here, for example, it's a 2D problem because the full 3D model, you can see that the thickness is much smaller than the width and the height, and so I'm possibly thinking that the analysis can be simplified to a 2D scenario. But that's kind of the number one rule, looking at the geometry. But then also the loads and your restraints have to act around the cross section. So here, for example, if I had something, let's say the load is actually acting something like this. So let's go ahead and apply, just to give you an idea, proof of concept. So if the load was, okay, this is already a 2D section. So let's go ahead and create a new simulation study on the full 3D model. So let's say the load was acting in plane, or perpendicular to the cross section. So from a geometry perspective, I can simplify this to a 2D scenario, but then now when I look at the load, the way this thing is loaded, I cannot do it because it's acting normal to the cross sections. It has to be the load. If the load is somewhere here or here around the cross section area, then yeah, that kind of is also that's kind of the requirement for doing or solving this problem as a 2D analysis or a plane stress problem. Okay, so if we can certainly send you some literature or information on when to use 2D analysis and how can you what are the different rules that we need to follow in order to be able to actually use 2D analysis. Well, lots of questions. Great. So let's see. So one of the questions is, can you specify whether the symmetry conditions are symmetric or anti-symmetric? So when you apply symmetry, it is actually symmetric. So I'm not sure if I need to know when you mean anti-symmetric. what exactly do you are you referring to? But here, when you apply symmetry, it's symmetry. So on a 3D model, basically we assume when you apply symmetry to a face, we assume that none of the nodes on the mesh which lie on that face can move in the normal fashion. Okay. Why can't you specify, so the next question is, why can't you specify two planes for symmetry boundary conditions which are not perpendicular? I model a large number of parts which have hexagonal or triangular symmetry. So I need to get a little bit more specifics about this because if you try to apply, if your question is, if you want to, if you take two cut planes which are not orthogonal, then if you try to apply symmetry, I know the program is not going to allow you to do that. But keep in mind, like, for example, if I want to apply symmetry on this particular face, then another option to do that would be to go here into fixtures, go to advanced fixtures, and maybe if you use symmetry, that's not going to allow you if the two cutting planes are not orthogonal. But what you can also do is, if it's a flat face, then you can just say, yeah, normal to that face, we don't want anything to move. If this is another symmetry plane, let's say, if just as an example, on the top face over here, I have another symmetry plane, then I can select that face and say normal to that face, it's not going to move. If I have, let's say, another flat face like this over here, okay, so you can clearly see that now the cut planes, in this case, are now obviously not going to be orthogonal. So let's select the top face, and then I'm going to select this angle face over here. And then in this case, I'm going to select normal to face is 0, and that is going to simulate the same exact behavior as you would select symmetry option. Okay, so I know there are different ways of applying symmetry, but the thing to understand about symmetry is all it's doing is it's preventing any kind of normal strain or normal displacements to the selected face. Okay, and so symmetry is the easiest way to do it, but if you're trying to do it on a bunch of non-orthogonal faces, you might actually want to use and if the faces are flat faces, then this is again a nice way to look at it. If not, you probably have to use the reference geometry option. Okay, so hopefully that answers your question, but if there's anything more specific, we can always take it offline and go from there. Okay, the last question is, why can't I specify two-plane symmetry? Okay, so that's a repeat of the same question, of the previous question, so both the questions came from the same person. So, but hopefully my explanation helped you a little bit to understand what symmetry does, and a couple of other ways of simulating symmetry on, especially when you're selecting non-orthogonal faces. Can you suppose, so okay, so I got one last question to answer, then we'll actually wrap this up just in the interest of time. So the question is, can you support periodic symmetric boundary conditions for Cartesian parts in addition to parts with polar symmetry? So we do have cyclic symmetry that can actually take care of your polar symmetry. We don't have anything for Cartesian periodic symmetry conditions. We can. So let's see if we can, yeah, so right now there's no direct option to do that, and again I would actually want to get some more detail on, when you say periodic symmetry condition, what would be a scenario in your case, in your designs, what's happening, maybe understand the physics a little bit better, and then try to see if there is a way to do that. But right now, so we have only cyclic symmetry, but again, for Cartesian symmetry, periodic symmetry, we don't really have a direct option for that. Okay, so I think those are great questions, but again, thanks everyone for listening in, and thanks for joining us today. I'll hand it back to Dana, who's probably going to wrap this up, and wish everybody have a nice day now.
Oh, hi. Okay, well, thanks everybody for joining us today, and I just wanted to tell you that this webcast plus all of our other webcasts are on our YouTube channel, and you can find the link on our webpage, trimexsolutions.com. It should be right there at the upper right-hand side. Ramesh, real quick, did you get David's email address right there? He wanted to follow up with you. And
Yeah.
saying thanks. Okay, fantastic. I just wanted to make sure that you did get that. All right, and like I said, thanks again for joining us, and everybody have a wonderful afternoon. Bye-bye.